On the morning of May 19, 1995, astronomer Douglas Richstone sat in a conference room at the Space Telescope Science Institute and listened to a presentation that made him uncomfortable. A colleague was showing Hubble Space Telescope data from the center of a galaxy called M87. The data showed stars near the galaxy's core moving at speeds that made no physical sense. Stars that far from any visible object had no business moving that fast under any known force. The only explanation that fit the numbers was an invisible mass of 3 billion suns in one point. Richstone remembered the moment clearly decades later. The room went quiet when the number appeared. Nobody said anything for almost a full minute, which is unusual for a room full of competitive scientists. What they were looking at was the first solid, dynamical evidence for a supermassive black hole. Not theoretical, not inferred from radio emissions, actual stellar velocities proving mass was there. The object at the center of M87 had been suspected for years, but suspicion is not the same as proof. In 1918, astronomer Heber Curtis had photographed a strange jet of plasma shooting from M87's core. He described it in a paper as a curious straight ray extending outward from the nucleus of the galaxy. Nobody knew what was producing that jet or what was powering it. The physics simply didn't exist yet. It would take another 7 decades before the pieces began assembling into a coherent picture. The jet Curtis photographed in 1918 is now known to extend 5,000 light-years from the galaxy's center. It moves at apparent speeds exceeding the speed of light, an illusion created by relativistic geometry. The plasma in that jet is accelerated by magnetic fields threading the innermost region around the hole. The energy source is the rotational energy of the black hole itself, extracted through those fields. A single object containing 6.5 billion solar masses powers a jet visible from 55 million light-years away. That object sits at the center of the image that would eventually shake the world in April 2019. But before the image, before the proof, before even the suspicion, there was Carl Schwarzschild. In November 1915, Albert Einstein presented his completed general theory of relativity to the Prussian Academy. He had worked on the equations for 10 years, revising them repeatedly as the mathematics resisted him. The theory described gravity not as a force, but as the curvature of spacetime produced by mass. A massive object does not pull other objects toward it through some invisible thread across empty space. It reshapes the geometry of the space around it, and other objects follow that geometry as they move. The more mass concentrated in one place, the more extreme the curvature of the surrounding spacetime. Einstein's equations were a system of 10 coupled, nonlinear partial differential equations, ferociously complex. He did not expect anyone to find an exact solution for months, possibly not for years. Carl Schwarzschild found one in December 1915, within weeks while serving in the German army on the Eastern Front. He was calculating artillery trajectories by day and solving Einstein's field equations at night. His solution described the geometry of spacetime around the perfectly spherical, non-rotating mass. He sent the result to Einstein in a letter from the front lines with a note of quiet satisfaction. Einstein presented Schwarzschild's solution to the Prussian Academy on January 13, 1916. He wrote to Schwarzschild that he had not expected the exact solution could be formulated so cleanly. Inside that solution was something neither man fully grasped at the time, a mathematical catastrophe. At a specific radius from the center, the equations produced values that became infinite without warning. Distances compressed to zero, time stretched to infinity. The mathematics simply broke and stopped working. Schwarzschild called this radius the Gravitationssphäre, the gravitational sphere of the mass. He assumed it was a mathematical artifact with no physical meaning, a singularity of the coordinate system. He died of pemphigus disease, contracted at the front on May 11, 1916, before the debate could develop. For decades after his death, the singularity in his solution was ignored as a mathematical nuisance. Most physicists assumed that real matter could never be compressed to such an extreme density anyway. Stars would stop collapsing before reaching that radius, stabilized by some physical pressure not yet known. In 1930, a 19-year-old Indian physicist named Subramanian Chandrasekhar boarded a ship to England. He was traveling from Madras to Cambridge to begin graduate study under the astronomer Arthur Eddington. On the voyage, he calculated the maximum mass a white dwarf star could have before collapsing further. He found a limit, now called the Chandrasekhar limit, of approximately 1.4 solar masses. Stars more massive than this could not be supported by electron degeneracy pressure after burning out. They would collapse beyond the white dwarf stage into something denser, something without a known endpoint. When he presented this result to Eddington at the Royal Astronomical Society in January 1935, Eddington laughed. He told the audience that Chandrasekhar's conclusion was clearly absurd and could be safely dismissed. A star could not collapse indefinitely. Nature would not permit such a ridiculous conclusion. Eddington was wrong, and Chandrasekhar spent years sidelined by the most famous astronomer in Britain. He would receive the Nobel Prize in Physics in 1983, 48 years after Eddington's dismissal. By then, the objects Eddington had called absurd were being detected across the observable universe. In 1939, J. Robert Oppenheimer and his student Hartland Snyder published a paper that changed everything. They showed mathematically that a sufficiently massive star would collapse without any stopping point. The collapse would continue past any stabilizing pressure until the star disappeared inside its own geometry. An external observer watching the collapse would see it slow, redden, and freeze at a critical surface. The collapsing star would appear to stop, its light shifting toward infrared and then to nothing. But from the surface of the collapsing star itself, the infall would continue at undiminished speed. The star would vanish from the observable universe while continuing to collapse in its own reference frame. Oppenheimer presented this result with no sense of drama. He found the mathematics clean and interesting. The paper was published on September 1st, 1939, the same day Germany invaded Poland and began World War II. It was largely ignored for nearly 20 years, while the world's physicists focused on other problems. The person who eventually forced the physics community to take gravitational collapse seriously was John Wheeler. Wheeler was a Princeton physicist who had initially resisted the idea of complete gravitational collapse. He spent years trying to find physical mechanisms that would halt the infall before the critical radius. By the late 1950s, after years of calculation, he concluded that no such mechanism existed in nature. A massive enough collapsing star would cross the critical surface and disappear from all external observation. In 1967, at a conference in New York, Wheeler searched for a term that captured the object's essence. He wanted something short, something visceral, something that communicated the physics without equations. Black hole appeared in his lecture almost spontaneously, and the audience immediately understood. The term spread through the scientific literature within months and has never been replaced or improved upon. But naming something and understanding it are separated by an enormous distance in physics. What actually happens at the boundary, the event horizon, remained deeply contested for decades after. To understand what an astronaut would experience crossing one, you first need to feel what gravity does to time, not as abstract theory, as a physical fact that affects every satellite orbiting Earth right now, today. Einstein's equations predicted in 1915 that clocks in stronger gravitational fields run slower than others. A clock on the surface of Earth runs slower than a clock at the top of a mountain, measurably so. The deeper you are in a gravitational field, the slower your clock ticks relative to an observer higher up. In 1959, physicists Robert Pound and Glenn Rebka at Harvard decided to test this prediction directly. They placed a gamma ray source at the bottom of a tower 22.5 meters tall and a detector at the top. The gamma rays climbing 22.5 meters out of Earth's gravitational field should lose a tiny amount of energy. The energy loss would be equivalent to a clock at the bottom running slower than one at the top. The predicted difference was 2.5 parts per quadrillion, a number so small it defied any intuition. Pound and Rebka measured it anyway, using the Mossbauer effect to achieve the required precision. Their result matched Einstein's prediction to within 10%, an extraordinary confirmation at the time. Later experiments refined the agreement to better than 1%, then to fractions of a percent. Gravitational time dilation is not a theoretical curiosity. It is engineered into every GPS satellite launched. The satellites orbit at 20,200 kilometers altitude, where Earth's gravity is weaker than at the surface. Their onboard clocks run faster than ground-based clocks by 45 microseconds per day due to this effect. A separate relativistic effect from their orbital velocity slows their clocks by 7 microseconds per day. The net correction is 38 microseconds per day, built into every GPS receiver's software automatically. Without this correction, position errors would accumulate at roughly 10 kilometers per day continuously. The entire global positioning system would become useless within hours if relativistic time were ignored. This is not exotic physics from the distant reaches of the cosmos. It runs on your phone right now. Near a black hole, this same effect does not slow time by microseconds per day. It stops time entirely. At the event horizon of a black hole, time dilation becomes infinite relative to a distant observer. A clock falling toward the horizon appears, from outside, to slow exponentially as it approaches. The falling clock's ticks become further and further apart, its light becoming redder and dimmer. The clock appears to freeze at the horizon, its last tick stretched across infinite external time. From outside, no object ever crosses a black hole's event horizon in any finite amount of time. The infalling object appears to asymptotically approach the boundary and hover there forever, fading. But from the clock's own perspective, from inside the falling reference frame, nothing unusual happens. The clock continues to tick at its normal rate, 1 second per second, as it always has, everywhere. The astronaut wearing the clock feels no lurch, no compression, no signal that anything has changed. They cross the event horizon in a perfectly ordinary moment that feels identical to every prior moment. This split, frozen from outside, normal from inside, is not a paradox or a contradiction in relativity. It is a precise consequence of how space-time curvature affects measurements in different reference frames. Both descriptions are physically correct, each valid from its own vantage point in the curved geometry. The external observer's universe and the infalling astronaut's universe share the same space-time, but different experiences of it. And this is where the story becomes genuinely strange, because the two descriptions lead to very different fates. The universe contains two fundamentally distinct categories of black holes, and they behave very differently. The first category is the stellar mass black hole, born from the death of a massive star in explosion. When a star between roughly 25 and 150 solar masses exhausts its nuclear fuel, its core collapses instantly. The collapse takes less than a quarter of a second, one of the fastest catastrophic events in the universe. The outer layers of the star are violently ejected in a supernova that can briefly outshine an entire galaxy. What remains at the center is a black hole with a mass between roughly 3 and 100 times the Sun. Its event horizon is tiny. For a 10 solar mass black hole, the horizon sits just 30 kilometers from center. 30 kilometers is the distance across a mid-sized city, compressed into the boundary of the unknown. These stellar mass objects are the most common black holes we have detected in the Milky Way galaxy. X-ray binary systems, where a black hole strips material from a companion star, reveal their presence. The stripped material forms an accretion disk that heats to millions of degrees and blazes in X-rays. LIGO and Virgo have detected gravitational waves from dozens of stellar mass black hole mergers since 2015. The first detection, on September 14, 2015, came from two black holes of 29 and 36 solar masses merging. They released more energy in 0.2 seconds than all the stars in the observable universe emit in that time. The merger was detected as a ripple in space-time, a stretching and squeezing of space itself at Earth. The stretching was 1/10,000th the diameter of a proton, detected across a 4-kilometer instrument. The second category of black hole operates at scales that make stellar mass objects seem almost quaint. Supermassive black holes inhabit the centers of most large galaxies, including our own Milky Way. Their masses range from 1 million to tens of billions of solar masses, compressed into a single region. Sagittarius A star, the black hole at the center of our galaxy, contains 4.15 million solar masses. It sits 26,000 light-years from Earth, hidden behind dense clouds of dust in the galactic plane. The Event Horizon Telescope collaboration published its first image of Sagittarius A star in May 2022. The image showed a glowing ring around a dark shadow, the same structure seen in M87 star 3 years earlier. Getting that image required correcting for the turbulent plasma between Earth and the galactic center. The plasma distorts radio waves the way heat shimmer distorts the view of a road on a summer afternoon. The team developed new imaging techniques specifically to remove this distortion from the final result. M87 star at 6.5 billion solar masses dwarfs even Sagittarius A star by a factor of more than 1,000. Its event horizon is 19.2 billion kilometers from the singularity, larger than our entire solar system. The distance from the Sun to Neptune, the outermost planet, is approximately 4.5 billion kilometers. The event horizon of M87 star extends more than 4 times that distance in every direction from the center. Standing at the event horizon of M87 star would be like standing at the edge of a structure larger than our solar system. And yet, and this is the detail that reshapes everything, you would feel absolutely nothing unusual there. This is the fact that separates M87 star from every stellar mass black hole in the catalog of known objects. The difference between a small black hole and a supermassive one is not merely a difference of scale. It is the difference between instant obliteration and a journey into the most alien place in the universe. The concept that explains why M87 star feels like nothing at the horizon has a name: tidal force. Gravity does not pull on every part of a body with equal strength at the same moment. It pulls harder on the parts closest to the source and weaker on the parts farther away. For a human body falling feet first, the feet are pulled more strongly than the head. This difference in pull across the body stretches it along the direction of fall. Simultaneously, the body is squeezed inward from the sides, perpendicular to the fall. The stretching and squeezing acting together is called spaghettification by astrophysicists. The word sounds absurd. The process it describes would be the worst death imaginable. For a stellar mass black hole of 10 solar masses, this process begins far from the horizon. Tidal force grows as the inverse cube of distance. It accelerates savagely as you approach. At 400 kilometers above the event horizon of a 10 solar mass black hole, the math turns lethal. Ulf Danielsson and colleagues at Uppsala University calculated this threshold precisely. At that distance, the tidal force across a 2-meter human body exceeds 10,000 Earth gravities. No bone survives this. No cell survives this. No molecule holds together at this force. The astronaut is pulled into a progressively thinner strand of atoms during the approach. Death arrives thousands of kilometers before the boundary everyone writes about and imagines. There is no consciousness remaining to observe or experience the actual crossing at all. The event horizon of a stellar mass black hole is a destination no living thing can ever reach. Now apply the same mathematics to M87 star with its 6.5 billion solar masses. Tidal force at the event horizon scales inversely with the square of the black hole's mass. Double the mass and tidal forces at the horizon drop by a factor of 4, not 2. For M87 star, the event horizon sits 19.2 billion kilometers from the singularity at the center. At that enormous distance, tidal forces across a human body are 10 billionths of Earth's gravity. That force is thousands of times weaker than the gravitational pull you feel standing up right now. An astronaut crossing M87 star's event horizon would feel nothing. Not a tremor, not a pressure. No instrument aboard the ship would register any anomaly at the moment of crossing either. The astronaut could be asleep when they cross and wake up on the other side without knowing. This is the detail that makes M87 star the only black hole a human could theoretically survive entering. Not survive permanently. Nothing survives permanently inside any event horizon anywhere, but survive long enough to be conscious, to observe, to experience what no human has ever seen. Researchers at Johns Hopkins University calculated survival times inside different black holes. Their paper appeared in Physical Review letters, and the numbers were startling when first published. For Sagittarius A star, at 4.15 million solar masses, an infalling observer survives about 12 seconds. 12 seconds of consciousness inside the event horizon of our own galaxy's central black hole. For M87 star, the mathematics yields something far more extraordinary than 12 seconds. The calculations show survival inside M87 star's horizon for approximately 18 hours at minimum. 18 hours inside a region of space-time that is causally severed from the rest of the universe. 18 hours in which no signal, no light, no particle sent outward will ever reach anyone. What does the astronaut actually see during those hours? The answer begins before the crossing. The approach to M87 star from 1,000 Schwarzschild radii out already distorts the entire sky. Gravitational lensing bends light from background galaxies around the black hole's enormous mass. Galaxies that should be hidden directly behind the hole appear stretched into arcs around it. Some appear as complete Einstein rings, full circles of light bent around the dark silhouette. The accretion disk surrounding M87 star blazes at temperatures exceeding 10 billion degrees Kelvin. Plasma spiraling inward at a significant fraction of the speed of light emits across all wavelengths. One side of the disk moves toward the approaching ship and appears dramatically brighter. The other side recedes and appears comparatively dim, a direct consequence of Doppler beaming. This asymmetry was visible in the 2019 Event Horizon Telescope image and matches the physics exactly. As the ship falls inward, the visual field begins changing in ways that have no earthly analog. Stars distributed evenly across the full celestial sphere start crowding into the forward direction. This is relativistic aberration, the same effect that makes rain hit a moving car's windshield. At high enough velocity, almost all visible light appears to originate from directly ahead. The photon sphere of M87 star sits at 1.5 Schwarzschild radii, 28.8 billion kilometers from center. At this radius, photons travel in circular orbits, trapped in a permanent ring around the hole. Light that entered this region millions of years ago is still circling, slowly spiraling inward. An astronaut near the photon sphere could see the back of their own ship in the ring's reflection. Photons from the vessel's rear orbit the hole and return to the forward cameras as ghost images. The effect is not metaphorical. The geometry of curved spacetime creates literal self-reflection. Below the photon sphere, the character of space changes in ways that instruments begin to register. The ratio of circumference to radius stops following the geometry learned in any school on Earth. Circles drawn in this space have circumferences smaller than pi times their diameter. Always. The deviation grows larger the closer to the singularity any measurement is attempted. The astronauts' instruments would begin showing small but consistent geometric discrepancies here. This is the first physical warning that the rules of the universe are shifting around the ship. The second warning comes from the visual compression of the sky as the horizon approaches. The disk of the visible universe, all stars, all galaxies, all photons, concentrates ahead, begins concentrating into a shrinking circle directly ahead in the direction of the fall. The sky behind the ship darkens, not because those stars have gone out or moved away. It darkens because light from behind can no longer find a path that reaches the ship's position. The geometry of curved spacetime has rerouted those photons away from the falling observer. The circle of the visible universe overhead contracts as the horizon draws closer and closer. At the moment of crossing, there is no flash, no alarm, no physical sensation of any kind. The circle is still there, still bright, still showing the entire observable cosmos in miniature. Light from outside can still fall inward through the horizon and reach the astronaut's eyes. But the topology of spacetime has closed. The crossing has happened. There is no going back. Not because the ship lacks the fuel to turn around and burn hard toward the outside universe. Because the direction back toward outside no longer exists as a direction in space anymore. Inside the event horizon, the singularity is not a place in space located somewhere below. It is a moment in time, a moment that lies in the mandatory future of everything inside. Moving toward the singularity is as unavoidable as moving toward tomorrow from today. No engine, no velocity, no physical force in the universe can alter this fundamental fact. Roger Penrose proved this in 1965, and the proof has never been successfully challenged since. Every possible future path through spacetime inside the horizon curves toward the singularity. The astronaut cannot escape, not because they lack technology, but because escape has lost its meaning. Inside the horizon, the sky has reorganized itself around the observer in a specific pattern. The entire visible universe, compressed into that shrinking disk, now sits directly overhead. Not in the direction of travel, not spread across the sky. Overhead, above, in the past direction. Below the astronaut, in the direction of the future, the singularity begins to assert its presence. It does not appear as a point of infinite brightness far below, the way intuition might suggest. It appears as a surface, a distortion spreading across the lower visual field like a darkening floor. Andrew Hamilton at the University of Colorado Boulder spent years building models of this view. His simulations, published between 2008 and 2018, showed the interior geometry in precise visual detail. The universe overhead glows with increasing intensity as the astronaut falls deeper into M87 star. More photons per second arrive from outside as the infall geometry compresses the incoming light. The stars overhead appear blue-shifted, their light compressed to shorter wavelengths. Objects that glowed yellow outside now appear white. Objects that glowed red now appear blue-white. The entire overhead disk brightens steadily, the universe above becoming more intense each second. This is not a lighting effect or an optical illusion produced by the ship's instruments or windows. It is a direct physical consequence of the astronaut's position and motion inside curved space-time. The photons arriving from outside carry information, specific frequencies, specific intensities. Each photon that arrives carried those properties from wherever and whenever it was originally emitted. A photon emitted by a star 1,000 years ago arrives carrying the star's spectrum from that era. A photon emitted 50 years ago carries a slightly different spectrum as the star aged and evolved. Inside the horizon, photons from different eras of the outside universe arrive in compressed sequence. Time outside continues to pass while the astronaut falls. But the photons don't arrive in order. They pile up, compress, arrive faster and faster as the geometry of infall accelerates everything. The astronaut is not merely watching the universe from a strange angle inside M87 star's horizon. They are watching time, the actual progression of time in the external universe, in fast forward. Not as a metaphor, as a physical phenomenon produced by real photons arriving at real eyes. How far into the future of the external universe can the astronaut see from inside the horizon? This calculation requires knowing how long the astronaut survives and how much time compresses. Papers from the Perimeter Institute for Theoretical Physics in Waterloo address this in 2019. The models show the compression accelerates exponentially as the singularity draws closer. In the final moments before the end, light from progressively later eras arrives faster and faster. The astronaut may receive photons from thousands or millions of years in the future of the universe. Whether those photons carry recognizable images or arrive as featureless radiation is uncertain. The blue shift would push the visible light into X-rays and then into gamma rays at extreme compression. A human eye cannot perceive gamma radiation. The cascade might become invisible before it ends. Or it might overwhelm the retina entirely, a blinding white flood with no structure to parse. The honest answer is that the final seconds inside M87 star remain genuinely unknown to physics today. Not because the question is unimportant, but because the mathematics reaches its limits before the end. General relativity describes the journey precisely until density approaches the Planck scale. At distances of 10 to the power of minus 35 meters from the singularity, quantum effects dominate. At those scales, general relativity and quantum mechanics produce contradictory descriptions. The two most successful theories in physics disagree about what happens at this location. General relativity predicts infinite density, infinite curvature, and the end of description. Quantum mechanics forbids true infinities. They always signal that the theory is being misapplied. The singularity in general relativity is not a real place. It is a failure of the theory. What actually exists at the geometric center of M87 star is unknown to every physicist alive on Earth. String theory suggests the singularity is replaced by a fuzzball, a quantum object with no center. Loop quantum gravity suggests space-time becomes discrete and granular at the Planck length scale. Some models suggest the infalling matter bounces outward again, forming a white hole in the future. None of these proposals has been tested. None can be tested from outside the event horizon, ever. The singularity is the universe's most sealed chamber, hidden from all external observation. Any measurement made near the center cannot escape the horizon to reach any instrument outside. The laws of physics, as we know them, were derived entirely from experiments outside black holes. They were tested in laboratories, in orbit, in particle accelerators, and across the solar system. Every verified prediction of every successful theory was made outside a black hole horizon. The astronaut approaching the singularity travels beyond the reach of every tested law. They are entering territory where the map runs out and only blank space remains on the other side. In 1974, Stephen Hawking sat down to calculate something he expected to be straightforward. He wanted to understand how quantum fields behave in the curved space-time near a black hole. The calculation was routine in ambition, a technical exercise combining two established theories. What he found instead overturned 30 years of assumptions about black holes in a single result. Black holes, Hawking showed, are not perfectly black at all. They glow with thermal radiation. The paper appeared in Nature on March 1, 1974, and physicists around the world read it twice. Some read it a third time, certain they were misunderstanding something in the mathematics. They were not misunderstanding anything. The result was correct, and the implications were enormous. To understand what Hawking found, you need to know something about the nature of empty space. In classical physics, vacuum means nothing. No particles, no fields, no energy of any kind. In quantum mechanics, the vacuum is not nothing. It seethes with activity at every point in space. Virtual particle pairs appear from the vacuum, exist briefly, and annihilate back into it. An electron and a positron blink into existence, last a fraction of a second, then disappear. This is not speculation. Virtual particle effects are measured in laboratories with precision. The Casimir effect, measured for the first time in 1997 at Philips Research Labs in the Netherlands, demonstrated that virtual particles exert real, measurable forces between metal plates in a vacuum. Two uncharged metal plates placed very close together are pushed together by virtual particles. The force is tiny but real, and matches quantum field theory predictions to extraordinary accuracy. Hawking realized that the event horizon does something unusual to these virtual particle pairs. Normally, both particles of a pair annihilate before either can travel any significant distance. But at the event horizon, one particle of a pair can fall inward while the other escapes outward. The infalling particle carries negative energy into the black hole, reducing its mass slightly. The escaping particle carries positive energy outward as genuine thermal radiation outward. From the perspective of a distant observer, the black hole appears to be emitting real particles. The spectrum of this emission is thermal, identical to radiation from a glowing object. The temperature is inversely proportional to the mass of the black hole producing the radiation. For a 10 solar mass black hole, the Hawking temperature is 6 billionths of a Kelvin. That is colder than the cosmic microwave background radiation that fills all of space today. A stellar mass black hole actually absorbs more energy from the CMB than it radiates outward. It grows slightly rather than shrinking. Hawking radiation is currently irrelevant for these. For M87 star with 6.5 billion solar masses, the Hawking temperature is incomparably smaller still. The evaporation timescale for M87 star exceeds 10 to the power of 100 years, a number without a name. The current age of the universe is approximately 13.8 billion years, which is 10 to the power of 10. M87 star will outlast the universe's current age by 90 orders of magnitude before evaporating. Hawking radiation from M87 star is physically real and simultaneously completely undetectable, forever. No instrument physics permits could detect radiation that cold against the warmer background. But Hawking radiation created a problem far more dangerous than the radiation itself ever could. If a black hole eventually evaporates completely, what becomes of everything that fell inside it? Every star, every planet, every quantum state that crossed the horizon. Where does it all go when the last Hawking photon escapes and the black hole is gone? In quantum mechanics, information cannot be destroyed, a foundational principle of the theory. Every physical state evolves from a prior state through perfectly time-reversible equations. Given the current state of any quantum system, you could in principle run the equations backward. You would recover the exact prior state from which the current state evolved, without any loss. If black holes destroy information, this reversibility breaks down everywhere at once. The principle that governs every atom, every particle, every interaction in the universe would fail. Not just inside black holes, the implications would propagate outward and infect all of physics. This became known as the black hole information paradox, and it divided physicists for decades. Stephen Hawking argued for nearly 30 years that information was genuinely and permanently lost. He believed the black hole interior was a separate region from which information could not return. John Preskill at Caltech disagreed. Information must escape somehow encoded in the radiation. The Hawking radiation must carry encoded information about everything that ever fell inside. In 1997, Hawking and Preskill formalized their disagreement as an explicit scientific bet. The stakes were modest, an encyclopedia of the winner's choice to be provided by the loser. The bet attracted attention because both men were serious physicists, staking public reputations. For 7 years, the wager sat unresolved as the community argued and computed without consensus. Then in 2004, at a conference in Dublin, Hawking stood up and conceded. He had found a new way to calculate the evaporation process that suggested information could escape. The information was encoded in quantum correlations in the Hawking radiation, in a scrambled form. He could not specify the mechanism, but accepted the conclusion and handed over a baseball encyclopedia. Preskill received his prize, but the paradox did not die with Hawking's concession. It deepened, because conceding that information escapes raised an immediate and more disturbing question. How does the information get out? What mechanism carries it from inside to outside the horizon? Nothing can travel faster than light. Nothing can cross the event horizon in the outward direction. The information must escape without violating either constraint simultaneously. But how? In 2012, 4 physicists at the University of California, Santa Barbara published a short paper. Almeri, Marolf, Polchinski, and Sully, known as AMPS, published their result together. Their paper showed that 3 assumptions, each individually reasonable, cannot all be true at once. The first assumption: information escapes the black hole encoded in Hawking radiation. The second assumption: general relativity holds at the event horizon. The crossing is smooth. The third assumption: quantum mechanics is valid everywhere, including near and inside black holes. AMPS showed mathematically that satisfying any 2 of these 3 assumptions violates the third. If information escapes and quantum mechanics holds, then general relativity fails at the horizon. If the crossing is smooth and quantum mechanics holds, then information is destroyed after all. If information escapes and the crossing is smooth, quantum mechanics itself must be wrong somehow. There is no combination of all 3 that produces a consistent description of the black hole. This became known as the firewall paradox, and it set the theoretical physics community alight. The name comes from what AMPS found lurking at the event horizon, if information truly must escape. For the escaping particle to carry information out, it must be entangled with earlier radiation. Quantum mechanics has a strict rule. A particle can be maximally entangled with only one system. If the escaping particle is entangled with the early radiation outside, there is a consequence. Its bond with the particle that fell inward, its virtual partner, must then be broken. Breaking that bond is not gentle. It releases energy at the horizon as intense radiation, not soft thermal glow at billionths of a Kelvin. Hard, energetic radiation at Planck temperature. Any astronaut reaching the event horizon would be incinerated instantly by this energetic wall. Not spaghettified, not frozen in time from the outside, incinerated at the moment of arrival. The smooth, featureless, undetectable crossing that general relativity promises would not exist. The firewall would replace it with an instant and complete destruction of any infalling observer. If AMPS are right, the journey inside M87's star ends not after 18 hours, but in the first instant. The astronaut never sees the compressed universe overhead, never watches time accelerate above them. They cease to exist at the boundary, destroyed by a wall of radiation physics demands be there. This is not a fringe position. AMPS are respected physicists, and their mathematics is solid. The firewall paradox remains unresolved as of 2024, more than 12 years after the paper appeared. The most brilliant theoretical minds alive have proposed resolutions that each break something. Juan Maldacena, at the Institute for Advanced Study, proposed one of the most radical answers. Together with Leonard Susskind at Stanford, he suggested that entanglement creates spacetime itself. The black hole interior, they proposed, is connected to the Hawking radiation outside by geometry, not by a signal crossing the horizon, by a wormhole threading through quantum spacetime itself. They called this ER equals EPR, linking Einstein-Rosen bridges to quantum entanglement directly. An Einstein-Rosen bridge is a wormhole, a throat connecting two separated regions of spacetime. Einstein-Podolsky-Rosen pairs are entangled particles, correlated perfectly across any distance. Maldacena and Susskind proposed these are the same phenomenon described in two different languages. Every entangled pair is connected by a microscopic wormhole threading the quantum geometry. The Hawking radiation in the interior are entangled, therefore connected by a wormhole. Information need not cross the horizon. The interior is already outside through the wormhole. This idea is extraordinary in its ambition and deeply contested in its physical interpretation. Whether ER equals EPR resolves the firewall, whether it makes physical sense at all, remains debated. Physicists have argued about it in papers and conferences for over a decade without resolution. The honest position is that nobody knows what happens at the event horizon of a real black hole. General relativity says smooth crossing, as it is said since Schwarzschild's wartime letter. Quantum mechanics says possible incineration, depending on how you resolve the entanglement. Both theories are extraordinarily well tested in their respective domains of applicability. Both cannot be correct at the event horizon, and we don't know which one fails there. The astronaut falling toward M87 star is falling toward exactly where this conflict is sharpest. They are the experiment that resolves the paradox, and they can never report the result back. Whatever they experience at the horizon dies with them inside the causal boundary of the whole. The firewall debate is therefore not merely a technical dispute between theoretical physicists. It is a question about whether the journey this documentary has been describing is even possible. If AMPS are right, in their strongest form, everything described so far ends at the horizon. If general relativity is right, and the crossing is smooth, the journey continues for 18 hours. What we know for certain is that we cannot know, not from outside, not with any instrument. The event horizon is not just a point of no return for matter and light and information and signals. It is a point of no return for knowledge, a boundary that physics cannot see past from outside. Everything beyond is inference, extrapolation from theories tested only in safer places outside. Assume for the rest of this account that the firewall does not exist. Crossing is smooth. Assume general relativity holds at the horizon, and the astronaut survives to observe what follows. Inside M87 star, a specific sequence of events unfolds according to the best mathematics today. The sky overhead compresses further into its glowing disk as the infall deepens inside. The blue shift intensifies as more photons per second arrive from the external cosmos overhead. What began as subtle brightening becomes, over hours of infall, an overwhelming brightness. Stars that were dim points appear as brilliant blue-white sources in the compressed overhead disk. Galaxies invisible before become visible as the blue shift pushes their emission into the optical. The entire electromagnetic spectrum of the cosmos is being compressed towards shorter wavelengths. Radio waves from pulsars arrive as microwaves. Infrared arrives as visible as ultraviolet. The astronaut receives the full output of the cosmos across all wavelengths, overhead and intense. This is not merely visual. The radiation arriving carries real energy into the observer's body. At some point during the 18 hours, the blue-shifted radiation becomes dangerously energetic. The photon energies arriving from outside climb toward X-ray levels as the infall progresses deeper. The hull provides shielding, but how long that shielding remains adequate is a genuine question. the astronaut may find themselves in an increasingly hostile radiation field hours before the end. Below the ship, the singularity's gravitational influence on the local geometry grows perceptible. Tidal forces that were imperceptible at the horizon begin building as the infall continues inward. The same relationship that made the horizon safe makes the singularity ultimately and completely fatal. For M87 star, tidal force becomes lethal roughly 600,000 kilometers from the singularity at center. That is still enormous, larger than the sun's diameter, but it is the final boundary now. Beyond it, the same spaghettification that kills near a stellar mass black hole begins again. The astronaut who crossed M87 star's horizon alive will not reach the singularity alive. Nothing does. The tidal stretching begins at that final boundary and accelerates without mercy toward the center. The singularity in general relativity is where density and curvature become mathematically infinite. But infinite values in physics equations are always signs that the theory has exceeded its validity. At the Planck scale, 10 to the minus 35 meters, spacetime stops behaving as a smooth manifold. General relativity's equations require spacetime to be smooth and continuous to function at all. At Planck distances, quantum fluctuations of spacetime geometry are as large as the geometry itself. You cannot use an equation assuming smooth spacetime to describe a place where it is not smooth. The singularity is where general relativity runs out of road and gives no further answer at all. What lies beyond? What the singularity actually is in physical terms remains genuinely open. String theory offers one answer to what the singularity actually is at the center of M87 star. In string theory, the fundamental constituents of nature are not particles, but tiny strings. These strings vibrate at different frequencies, each corresponding to a different particle type. At the Planck scale, where general relativity fails completely, string theory provides new geometry. The singularity, in several string theory models, is replaced by a fuzzball of quantum strings. A fuzzball has no center. It is a dense quantum object occupying a finite volume without a point. There is no infinite density inside a fuzzball. There is no singular geometric center at all. The infalling astronaut would not hit infinity. They would hit a quantum foam of strings instead. What that experience would feel like, whether feel like even has meaning there, is unknown. Loop quantum gravity offers a different resolution from an entirely different theoretical base. In loop quantum gravity, space-time itself is not continuous. It is made of discrete quantum chunks. The smallest possible region of space is the Planck volume, 10 to the minus 105 cubic meters. Below this scale, the concept of spatial distance loses all physical meaning by construction. The singularity cannot form in loop quantum gravity. Space cannot compress below Planck volume. Instead, the infalling matter accumulates at maximum density and then bounces outward again. The interior, in this picture, eventually becomes a white hole, the time reverse of infall. A white hole expels matter outward and cannot be entered. It is the mirror image of infall. Some theorists suggest that the white hole emerges in a different region of spacetime entirely, not in our universe's future, in a new region of spacetime causally disconnected from our own. The infalling astronaut would pass through a quantum bounce and emerge into a different spacetime. Whether that spacetime resembles our universe or is something utterly alien is not yet calculable. These are not fringe ideas. They are serious proposals from physicists at major institutions. They are also untestable from outside the horizon, which is what makes the singularity maddening. Every proposal about the singularity is permanently shielded from any external verification. The cosmic censorship hypothesis, proposed by Penrose in 1969, addresses this shielding directly. Penrose conjectured that singularities are always hidden inside horizons, never naked in space. A naked singularity, visible from outside, would represent a complete breakdown of predictability. At a singularity, all laws fail. If one were visible, physics itself would appear to break down. Penrose argued that nature always hides singularities behind event horizons, out of all sight. The conjecture has never been proven. It remains one of the major open problems in relativity. Numerical simulations have found configurations where naked singularities seem to form briefly. Whether these are genuine violations or artifacts of idealized mathematical setups is debated. If true, censorship means the singularity is permanently sealed inside M87 star's horizon forever. Whatever happens at those last 600,000 kilometers stays inside the horizon forever after. Now consider what the 18 hours inside M87 star actually mean from a cosmological perspective. The universe outside the horizon does not pause while the astronaut falls through the interior. Stars continue to burn, galaxies continue to rotate, civilizations continue whatever they are doing. Time outside flows forward at its normal rate throughout the duration of the astronaut's journey. But the photons those external events produce can still fall inward through the horizon and arrive. Below the horizon, the astronaut continues to receive light arriving from the external universe. That light arrives blue-shifted, compressed to shorter wavelengths and higher frequencies. The compression means photons from later external times arrive faster than originally emitted. An event 1 year after crossing produces photons that arrive before a year has passed inside. Infall geometry compresses the arrival times of external events progressively as depth increases. The Perimeter Institute modeled this compression in detail in papers published in 2013 and 2019. Their calculations show the compression factor grows without bound as the singularity approaches. In the final seconds before tidal forces kill, photons from increasingly distant futures arrive. The precise future visible depends on M87 star's mass and the specific infall trajectory chosen. For M87 star, the numbers suggest visibility of thousands of years of external cosmic time ahead. Whether thousands or millions of years are visible depends on calculations not yet completed. The blue shift at those depths pushes visible light into the X-ray range. The eyes cannot respond. X-ray photons do not trigger the retinal cells that produce vision in any known biological system. The visual experience, if any, would be a featureless white blaze rather than structured images. The radiation carries the information regardless. It exists whether any eye can parse it or not. The entire future light cone of cosmic history converging downward onto a single falling point. On a single ship. On eyes that cannot even perceive the frequency in which the future arrives. There is something unbearable about this when held as a physical fact rather than a metaphor. The universe delivers its future into the black hole, and the recipient cannot read the message. The most extreme information density anywhere, arriving at the least capable receiver possible. Consider also what the people outside the horizon see during those 18 hours of interior time. They see nothing. The astronaut crossed and vanished from the entire observable universe at once. No signal escaped as the ship fell past. The last photon emitted arrived just before crossing. To an external observer, the ship's image froze and faded at the horizon boundary as it approached. It did not cross. It appeared to asymptotically slow and redden and dim and become invisible. The crew experiencing 18 hours inside appears, from outside, to have never crossed at all. They are simultaneously 18 hours into their final journey and frozen eternally at the horizon. This is not a paradox. It is a precise consequence of how event horizons work in relativity. Two observers can have irreconcilably different but equally valid descriptions of the same event. The mathematics producing both descriptions simultaneously is among the most beautiful in physics. But beauty does not resolve the human meaning of what these descriptions actually say. A person who falls into M87 star is gone from the universe of their origin at the moment of crossing. Gone not because they died, not because they moved too far away, not because communication is slow. Gone because the causal structure of space-time has permanently separated their future from ours. No technology resolves this. Not faster than light, not wormholes, not quantum teleportation. The separation is written into space-time geometry by the same equations that govern GPS clocks. It is arguably the most absolute isolation any physical object can experience in this universe. More isolated than a galaxy beyond the cosmic horizon, which might at least share causal history. More isolated than the most distant quasar, from which photons still technically reach us today. Inside M87 star's horizon, there is no, technically, there is simply no causal contact at all. And yet from inside, the universe is still entirely visible overhead in the compressed, glowing disk. The astronaut is isolated from the universe, but can still see it, receive from it, observe it. They are like someone watching through a one-way window, unable to knock, signal, or call out. The universe performs its entire future for an audience of one who cannot respond in any way. This asymmetry, seeing without being seen, receiving without sending, has no human analog. No situation in ordinary life captures what it means to observe with no possibility of reply. The closest comparison is reading history. You receive information you cannot respond to at all. But history is in the past. Inside M87 star, the astronaut receives the future, arriving as present. In April 2019, that orange ring appeared on screens at press conferences across the world. Most of the world saw a blurry circle and understood it as a photograph of something far away. What it showed was the shadow of a region where the rules of the universe themselves transform, where time and space exchange roles, where the future becomes a direction rather than a dimension, where the cosmos concentrates overhead into a shrinking disk of overwhelming blue-white light, where relativity and quantum mechanics, the two pillars of physics, openly contradict each other, where a human could spend 18 hours observing what no human has ever seen or will again, and where none of that observation could ever reach anyone, anywhere in the observable universe. That 2019 image was 19.2 billion kilometers of event horizon compressed into a fuzzy orange ring. Every pixel of that dark center is a pixel of territory from which no information has ever returned. Every photon in that ring traveled through the most extreme curved spacetime ever photographed. The scientists spent years calibrating instruments, flying hard drives across continents, building algorithms to reconstruct a picture from interference between radio telescopes, separated by the diameter of the entire Earth, achieving angular resolution never achieved before. They were trying to photograph the invisible, and they succeeded in capturing its shadow. The shadow is real. The mathematics describing what lies inside the shadow is real and tested. What no mathematics can currently describe is what actually happens at the center of that shadow. That gap between the tested theory and the untestable interior is where physics currently lives. It lives there not from lack of effort, but from the fundamental geometry of what black holes are. The universe has arranged its most extreme laboratory to be permanently sealed from all view. Every experiment resolving the deepest questions of physics happens inside that sealed room. Every result stays inside that sealed room for the rest of the universe's entire existence. The first humans to enter a black hole would not merely be first to cross an event horizon. They would be the only beings in the observable universe to ever know what actually happens inside. They would carry that knowledge for somewhere between 12 seconds and 18 hours. Then the knowledge ends with them, sealed behind the most absolute boundary nature has made. Outside, the universe continues. Stars burning, galaxies drifting, time passing as always. In the overhead disk above the ship, all of that arrives as compressed blue-white photons. The entire future of the observable universe pouring through the event horizon to meet them, delivered to the one place that cannot send anything back. The first humans to enter a black hole would never come back. Not because they lack the fuel, not because the journey was too long or the technology not yet ready, or the will not sufficient. They would never return because the concept of return ceases to have meaning at the horizon. The direction back toward the universe does not exist inside M87 star's horizon as a spatial direction. It exists only as the past, and nothing in this universe travels backward through time. What they see in those final hours, no human framework of experience has prepared anyone for. The entire future of the cosmos delivered into a single shrinking point of blue-white light. A universe spending its entire future communicating to someone who cannot answer back at all. That image, future time arriving as a death sentence in compressed photons, has no equal. It is the universe's most extreme experience, available only to those who can never describe it. Whatever it is, firewall or smooth crossing, fuzzball or bounce or genuine infinity, It is the place where human knowledge ends and something else begins that we have no name for yet. Thank you for following this journey to the edge of what physics knows and what it cannot yet say. If this raised questions you want to pursue further, subscribe and stay for what comes next. Your curiosity about the unreachable is the only instrument pointing in that direction at all.